Okay, I think we'll get started. We're getting always a little bit quicker setting up, I hope, every time. So last week we were talking about what is a game, and we talked about what is an engine. We sort of talked a little bit about how engines were, like game engines specifically as a piece of software, were not really around from the beginning. It was really something that happened over time. And so more and more emphasis has been on building that magical box that takes in some data and then renders a world that you can interact with. And so with that magical box, you can create pretty much any world imaginable. So it's kind of a high order actually to make a box like this, to make a box that is this capable of producing a simulation of that quality and of that type of, that supports that kind of interactivity that people expect from a game. So now we'll be looking a little bit more under the hood, trying to understand what's inside that magical box or black box. But first, before I go into the actual components inside that box, I want you to think about it a little bit more yourselves. So what I'm going to start doing today, and just leave this picture as a background picture. I want you to take out a pen and paper or maybe a laptop. I don't know. I don't like seeing a lot of backs of laptops. But anyway, if all of you right here in the room can kind of pair up, just be like people next to you, sit a little bit closer, and for the next few minutes, I want like a group of 2 or 3 of you, each of you, to sketch out a few boxes that you would think would be parts of a game engine that you would develop. Like if you had the task of making that box here in the middle, what are, from the point of view of an architecture of that box, of a software architecture for that box, what would be the main parts inside it? Another way to put it is that if you have a large team and you're all going to be working on making that engine, you kind of want to split up the tasks between the team members. What would be the natural borders, natural segmentation of the team uh, in that development effort? So I want you to come up with maybe anywhere from like 6 to 10, 12 boxes and label them for the main functionality of that box. So it's also like, here's the game engine, these are the parts of the game engine that we need to develop and need to worry about. So can you do that right now? Have you found anyone next to you? Maybe you can switch tables or something like that to, or hook up with someone here. Otherwise, we'll just have at least a couple of people. Because I want you to discuss this. I want the 2 people or 3 people that are together to actually like discuss this and come to an agreement about what are the most important boxes in that diagram. So start discussing now. I'll give you maybe like 10 minutes at most to do this. En we willen bara finna ett hål hérna. So has everyone gotten at least 5 boxes, maybe? Five, everyone? Okay, let's just stop there and keep track of these 5 boxes that you've put it down. And I want you to actually, throughout the class today, to kind of go back to those boxes and check them off if we discuss them. And if we have come to the end of the class and we have not discussed one of your boxes, I'd really like to know about it. Because I really want to see what ideas are out there for things that might not be covered by, the book or what things that I'm talking about. So it's nice to be able to capture everything. And but first, actually, I would like to know if there were there any disagreements or like heated discussions about what should be there and what should not be there. Anything like that? or anything surprising, not so much. All right, well, let's go through this and come back to this after we discuss some of the boxes that are in this picture. This is the runtime game engine architecture picture. It's in the textbook. I mentioned last time that this was a bit like our map for the course. That's kind of one way to put it because we have a lot to cover, but we're not going to be able to cover all of these things. But these are the boxes that try to cover almost all the aspects of a game engine, what it has to be able to do. And you could also argue that this is not, well, it is, certainly is not all the game engine because we have some stuff at the bottom that is outside the game engine, and towards the top we have something that is also outside the game engine, which is basically the game itself. So the game engine in this massive diagram is the middle portion, the biggest part of this. We have like, yeah, you're not going to be able to read this, but I'll tell you right now, we have like the operating system and stuff down here, and then we have all kinds of layers to this, and then we have a game there at the very top. Um, did you think at all about like how you would organize your diagram? I don't know. I mean, it's a very short time to sketch this down, but is there any particular order in which you would put these boxes if you're building an architectural diagram? Does the, you know, would it be interesting to draw them in a particular order or organize them? Any, do you know how, what kind of order the boxes are in here, in this picture? I don't know if you have looked at this picture at all in your book, but there is an order here. Can you guess what that is? So the location of a box in this picture does matter. Any ideas about what the vertical axis here is? Low level and high level. Makes sense. Yeah. You can even be a little bit more strict than that. Or okay, maybe explain like what it means to be low level versus high level. Abstract, yeah. More abstractions maybe, yeah. Abstracting away from something else that you don't want to deal with, for sure. Uh, and there's another thing that at least is being attempted here, which is kind of important, and that is basically on what you depend, like a dependency direction. So the things that are higher up, they depend on things below it, but the things below do not, and this is important, the things below do not depend on anything above them. So you can sort of strip away everything from the top and things below still work. They can be tested without the stuff above it. So that's kind of important. Of course, it makes testing a lot easier because you can always like strip it down to those basic bare bones and still make sure that those this kind of plumbing works before you add stuff on top. If you get like a cycle in all of this, if you have a circular dependency, then that becomes a nightmare to fix and debug. Everything has to be running at the same time, and you can't really isolate the problem that easily. So that's one way to think about it. But also, like the stuff at the bottom is something that can be reused again and again for different things at the top. So yeah, so this is one way that these boxes have been organized. But today I'm gonna talk about some of these. I'm gonna mostly stay just with the bigger areas. You see that there's sort of a slight coloring in here that denotes certain areas in this system, and we'll kind of just go through that a little bit. Um, and I want to start with the very lowest part, which really at the very bottom we have the hardware itself. Uh, and this is like different platforms. Of course, you have the consoles, all of the consoles there. You have a PC, a Mac, whatever. So those sit there at the bottom, and they also have some specific devices attached to them. Controllers that can be different between different games or what you support. All of this hardware somehow has to be accessed, and it is accessed through pieces of software that you know as drivers. And usually the drivers are being supplied by the hardware manufacturer, or at least in collaboration with the operating system people. So you don't have to take care of talking to the hardware usually yourselves. You are typically talking through some kind of software that already masks away the specifics of a hardware device. Even devices that look the same, function the same, and everything, the actual hardware might be different, and you don't want to worry about that. Some kind of speeds of communication, things like that, you don't want to worry about those things. So that's all taken care of with drivers. And drivers kind of bring them into the operating system through kind of a standard interface that now you can use the operating system to talk to these devices. Um, so the operating system here is below the engine. I mean, it's running on top of the operating system. But it was, I mean, for game machines and consoles in the older days, there was hardly any operating system to speak of. I don't know if you have like would you actually take your PlayStation 1 and fire up the operating system? Not really. You wouldn't really have that kind of generic system that you would be starting up in and then loading your game. You would just load your game immediately. But you can't say that there's like no operating system. There has to be some software, again, something to talk to the hardware down here. And so usually the operating system would have been just a small slice of software that was maybe loaded at the very beginning, and then the game immediately loads on top of it. So that thin layer there does exist even if you don't, as a user, experience an operating system. But this is changing quite a bit. I mean, have you, like, I don't know if you have any of the newer consoles. Do you have the feeling that there is some software running there in the background that is not the game? You all experience, and I mean, sometimes this can be a major like annoyance because there's something like what can happen when you're playing a game. Like, how do you become aware of the operating system? Sorry? It tries to, exactly. That's probably the biggest annoyance. Like, oh, everything slows down. Like, oh no, it's updating some. Exactly. That's one of those things. I mean, the operating system is one of the tasks of the operating system is to divide the time or the CPU or between different tasks. And sometimes these other tasks, they just come in and they want to do something really bad. And then, especially if it involves some kind of I/O, then that's going to be slowing down other things that are going on. So yeah, updates and also like staying in touch with like your community. So all of these things that have to do with connecting you to some kind of a player base or some kind of a central thing. Maybe like getting notifications about your friends playing something. All of that stuff is going through a generic system in the background. And unfortunately, the game doesn't have any control over this. Like the game engine even that you're using, they just kind of have to deal with it. That there is such a thing taking over. On PCs, of course, the operating system has always been there and been a massive part of the whole system. And so the operating system is something that you have to just, it exists and you have to think about, but sometimes you can't do much about it. Um, So the next layer up from the operating system that is sort of getting closer to that magical box that does everything for the game, it's called the third-party layer, third-party SDK, software development kit layer, APIs or whatever. So this layer contains all, like you've probably seen many of these logos when you run a game. You've seen like powered by this and that and that and that, this SDK. So this is all third-party developers that have isolated some kind of a problem that a lot of people want to solve in game engines and to solve it for them. And say, hey, just get our package and you don't have to write this code yourself. Just stick it in and you're good to go. And you probably know some of these things, right? Like what does Havoc do? You know that? Physics, yeah, exactly. Implements all the laws of physics. basically how forces can be applied to objects, game objects in the world, and how that affects the object behavior. Forces like gravity is something that is like really popular to add, but also forces like someone actually slamming into someone else. Yeah, so the laws of physics have been packaged very nicely up there. Uh, we have Havok and also the PhysX, which is like the NVIDIA version of the physics engine. Originally, the physics package, which is now actually a part of the Unreal Engine, so you don't actually have to keep that as a separate package. But you can bring it into your own software development if you want. But physics was originally created as an API for a physics card. I don't know if they I haven't heard much about these cards anymore because now the GPUs can do pretty much anything, but there used to be like a separate physics accelerator card being proposed by NVIDIA at some point. And that was the interface for that, to do the physics on a specialized CPU or process unit. Now I can see the stream is a little bit, uh, I might have to restart the stream. It might have broken here, just here. No, okay, it seems to be okay. Just the screen over here is not seeing it. Yeah. Now other libraries that people have been using is C++ classes, data structures, optimized optimized algorithms or data structures. So the Boost library of C++ or C++ has been very popular in bringing in pretty high-powered C++ code. Um, we have APIs for making games. There probably is something like a C++ library that Facebook is using internally, but also allowing other people to use. A lot of well-designed C++ code. Have you seen this label here? This actually, I've seen less and less of this logo when I start up games today. Do you know what this is mostly? Cutscenes, yeah, exactly. This was basically a video player, or a media player that a lot of game engines incorporate so that they could show cutscenes between levels or something like that. So it's just basically like you could play an MP4 video or something. But now people are more and more relying on just in-game cutscenes. So they're not really recording them ahead of time, so I see less and less of this. And Granny 3D is actually a very well-known 3D animation package. So you probably, I don't know, actually, I've not seen this logo anywhere, so, but it is being used by a lot of engines that incorporate it. And Euphoria and those types of things are animation tools that actually use biophysical animation. So it's like you can sort of like calculate the animation from the configuration of the humanoid bodies and how they. It's actually used a lot in sports games where they like crash into each other and you have to figure out so where all the limbs gonna be after the crash. And that's all calculated by this toolkit, Euphoria. So all of these things, this is just a sample of it, but you can usually find a solution to many interesting problems if you look for third-party tools. But why are they? You can see that there are some of these tools are pretty high level. I mean, you can even think of like some of them are doing like AI or something like that. But why are they all here at the bottom since they are so high level then? Exactly, they're not dependent on anything above. So this is actually a layer that is kind of like completely, what do you say, it's ignorant of how we are using them. So anything above, anything we build on top of it, doesn't really concern any of these packages. So that's where they're down here. So, but so when we then move up from this, Then we are getting finally into our own code. And you might actually start with a layer that completely abstracts and isolates you from all the specifics below. I mean, you can create one layer here that is like called a platform independence layer. And there are two kinds of things you might want to isolate yourselves from. One, what would that be? Like if you, what maybe one of the biggest things if you're thinking about moving your game between actual game platforms, you have to isolate yourself from the specifics of that platform, obviously. And a file system is a good example. A file system on, like, say, a PlayStation would be very different from a PC, where all the media is being stored. Like, so that's one thing you might want just to abstract and say, I'm going to make my own file system with all the ways in which you can find files and read files and write files that then has just a little bit of like a plugin for each of the platforms below. So that's one isolation, is just the operating system essentially that you're isolating yourself from. The other thing you might want to isolate yourself from is actually these tools. So you cannot necessarily guarantee that they will be around forever, or you might at some point get a better deal, like, hey, like here's a physics system that is free, or something like that. So why am I paying all of this to use that, you know? So at a later point, you might want to say, oh, I'll just, switch that thing out and use this other cool tool. In order to do that, you kind of have to isolate yourself again from that tool if you can, so that you don't like bring that tool into your game engine all the way to the top. It's going to be very hard to cut it out. So yeah, the platform independence layer is kind of to make you really safe to all of the mess and changes and stuff that goes on down here. So yeah, file system, networking, how the clocks work, and things like that, and basic graphics wrappers, for example. Actually, Ochre is doing this pretty nicely. You see, Ochre is able to switch things, like for example, going from direct 3D, um, or to OpenGL and things like that. So like the graphics API is isolated in Ochre, which is kind of neat. Now above this, you have that what here is called core systems. Another way to describe that white like middle layer here is utilities. And I think all of you are familiar with this. Utilities, like you might all, I don't know, most of you might actually have some kind of a little, keep a little bit of a library of functions you use again and again and again. And like for new projects, you just bring that in and you can, hey, yeah, I don't have to write again how I do like something pretty trivial or maybe something complex. So here is basically all kinds of core systems that have been written in the programming language of choice here, which is usually C++, to just take care of this general stuff. Like for example, assertions is like a system that allows you to check for whether assumptions hold in your code or not. Like you are actually expecting something to be a real pointer and not a null pointer, and you put an assertion in there that alerts you or breaks everything or logs whenever that pointer becomes a null pointer. So it's like a way to make sure that your code is actually running on data that is the way that you think it is. Um, Profiling, gathering information about execution times, being able to clock different functions. It's a nice thing to have the ability to do that. Uh, Being able to load files in the background, streaming files in the background without having to halt execution when you load a file. That's pretty handy. Um, so you see it, and I think there should be here memory allocation. So we will actually talk about that later also, is memory allocation. Sometimes you don't want to just use the operating system's memory allocation and handling, so you actually write your own memory handling. and that's a good thing to have in here. So this layer is kind of like a power tools for the game developer and game engine developer. And in this course, we will actually look at some of these, like what are some very useful tools that you might want to implement. So going up from there, we now have something that is starting to look a little bit more gamey somehow, because now we are looking at how to bring all of the game assets into the world. And here it is called a resource manager, uh, which kind of is this layer that allows you to just say, I need this character, and the layer and this kind of manager just, okay, I'll bring in the character for you and get it into memory, and this will be the ID that you will use to make the character do something, whatever. So it completely just makes it easy to bring in all these game objects, create all these game objects. Um, Often there is literally a resource manager, like an actual class that you talk to. Like in Ogre, there's a resource manager class in Ogre. You talk to that class and you say, I need something of this type or that type. And that single manager is able to deal with all of these different types. But in some cases, there's not a literal class or literal uh, subsystem called a resource manager, but rather you have ways to bring in different assets through some kind of a set of classes that each represent different types of assets. But this is just to give you some idea of the types of resources that you might want to bring in. Of course, 3D models. Don't forget fonts, for example. That's a resource that you might have to get in. Um, Physics parameters, a whole map, basically like a specification for the locations of all of these objects, and so on. So here you have, and of course there should be audio there as well, and things like that. Okay, so now the things above this can just talk to this part to bring in what they need. Now, like you see the little mini map up there, so we're actually kind of jumping to a big piece here. And this piece is all the rendering parts. Um, I think before we go into this part, we should just break for 5 minutes. Let's do that. So it's a good place to stop for 5 minutes. Let's go back in 5 minutes, around 11, 11, a couple of minutes over 11. Cos'è? Yeah. All right. Keep it going. Definitely. Okay. Get started again, and because we're talking about basically the rendering subsystem and the different parts of the rendering system, I figured I would just quickly show you that rendering can be a kind of a complicated thing, I guess. So let's say that we have some kind of a scene with objects and mountains and I don't know what. Like maybe this object is actually a house, so it has like windows and there you can go inside the house and there's a path there and whatever. So this is an entire world of objects. And then when we want to render these things, we kind of have this screen here that the player is looking at. And we have to bring these things onto that screen. And I mean, you definitely will have some kind of a camera inside the world that is looking out. And you kind of want to show the perspective from that camera. Like, what does that camera see? You want to write that on this screen here. Um, And we have to break down this problem into little kind of parts so that it can become manageable. And one of the things that we have to really understand, of course, like every single object here in the scene is typically composed of small units that we call polygons. And typically those polygons would be triangles, so we can usually like divide all of these objects up into these kind of triangles. So we can break them all apart into triangles, and then we have fast ways of taking a triangle and turning it into pixels on a 2D plane, like that monitor over here. But really handling all of these triangles for all of the objects, let's say these mountains as well, is quite time consuming. So pretty much no matter how fast you are at rendering these triangles, you definitely want to get rid of as many of these objects as possible before you actually let the rendering start. So this is the reason that you have this separation here between what we call a low-level renderer and then what is above it called the scene graph or culling optimization. So these are two separate systems or separate parts of the rendering system, where the low-level renderer is really good at handling these triangles. So you can grab a ton of these triangles and throw it into the low-level renderer, and it will get those triangles on the screen really fast. But you don't want to have it spend time on triangles that will not end up on the screen. So you need another system to figure out what exactly should be inside this. What exactly is sort of the camera looking at any given time. And that is the role of the higher level, like the culling optimizations part. To say, okay, these mountains, we don't care about them, we don't care about these objects or those objects. And then that higher level then creates what is called render packets. That are like, here are exactly the triangles I want you to render, and then this one grabs them and does a really fast rendering of them. So inside this circle here is what is called the potentially visible set of geometries that we then work with. It does not mean necessarily that all of those triangles will end up on the screen in the end. There might still be a little bit of like cutting off things happening here. For example, just the borders of the screen may be such that there's like a half a triangle inside the screen and half a triangle outside. So it's the low-level renderer that will then cut that triangle kind of nicely along the edges. So the detailed cutting is still happening inside the low-level part. But just kind of tidying up the world, optimizing is kind of the higher level. And we already saw that in Ogre you can change scene graph managers. And you can do this type of optimization depending on what kind of world you have, whether it's an indoor world, outdoor world, things like that. So you will actually see that in that picture here. In the optimizations, you have an LOD system. That's a level of detail system that picks the right number of polygons, really, for a particular object. So maybe these mountains are visible from the point of view of the camera, but the camera is so far from these mountains that it makes no sense to send in thousands of triangles for these mountains. So because of the distance is that far, the LOD system will say, no, I'm just going to use the like really rough model of a mountain with like 4 polygons and send that in instead. So reducing the number of polygons that then the low-level system gets. That's the role of the LOD system. And here's the PVS is the potentially visible set, which is like calculates or finds out what is kind of what are the objects that we care about right now. And the low-level renderer, like I mentioned, is like really good at rendering these specific polygons, and then also bringing in the different settings that affect that specific polygon. So it's drawing the polygon, it's figuring out what the colors are in the pixels inside that polygon or triangle, and that is completely dependent on the materials and lighting. And so it has to be able to understand what shader should I use for this polygon. And this is all the information that comes in along with the package. I mean, a rendered package is basically a combination of a polygon and some settings, some context for that particular part. Like, exactly like what lights are affecting that specific polygon. Okay, so then we have some things that even further up. We have visual effects, and they can be all kinds of visual effects. I mean, you can have an explosion effect that actually relies on a particle system or something like that. So that's kind of a specialized thing. In that case, a particle system that generates particles for explosions, the particles actually have to be rendered. So an particle system provides input into a low-level rendering system. So it will have to hand the rendering system triangles again to paint. So even if it's high up there, it actually talks right down, talks to this during the rendering of the scene. But some of the visual effects, so let's say like the particle system, they kind of insert themselves in here and then they get put on the screen. But there are some visual effects that are applied after you got the picture on the screen. So it's almost like you have another screen here. The first screen is the one that is being rendered on first, but it's not the screen that the player sees. There's one additional step, which is the post-processing that takes what was rendered and then does some kind of tricks to it, like filters and things like that, like you would see done in Photoshop or something like that. And then creates a second picture, and that second picture has all the effects in there, which could be like blooming or high dynamic range tricks, or even shading, shadows and things like that can be applied in post-processing. So in the end, what you get is something that looks really real, and those effects have been applied to only a very, very small part of the whole scene. Literally the part that you are looking at, and not to any of the other parts. So visual effects is like a bag of different things. So you see their post effects that's applied to the screen, and you see the particle system there and detail systems. They actually insert themselves into the rendering. And then at the very top, you have rendering that is concerned with the two-dimensional 2D screen or GUI on top of everything else. And that's sometimes you have, yeah, it's kind of like an afterthought maybe. Like you have everything up and running, but hey, wait, we forgot, like we need a menu or something, right? Or heads-up display or something. So you have to solve that, adding a layer kind of on top of this, which would be, you can draw on. Often that is done by creating like a separate camera that is it's an orthographic camera, so there's no perspective in that camera. So distance from the camera does actually not matter. So it doesn't matter actually at what distance you place these things, they always look like they're just right there in front of you. They don't scale it and become smaller or bigger by distance. And they are usually attached to the user, or it's just completely a fixed position. So like the main menu just pops up and you always see everything on it. So so yeah, that's the highest up there level. So with these four rendering subsystems, you more or less covered the parts of getting graphics on the screen. Some of those graphics, they of course come from other parts of the system. And if we go here to the left a little bit, we see a big system here in the middle that is all about animation. And animation can be sort of a complex topic and be broken down into, again, many subparts. The animation system that you're seeing here is the skeletal animation system, but there are other types of animation systems for games and game engines. And I don't think we have in here, do we have a morph system? I'm not sure if that's actually being shown here, but many games apply also a morph animation, but that's a kind of a separate process. But the skeletal animation system is basically you have a set of bones in every character. So every character has a skeleton literally. And then all of the movements that you're doing in the game, whether they are procedural movements that come from a physics engine or whether they are keyframe animations that an animator has carefully done, or maybe motion capture, those things all affect the skeletons. They don't actually handle the look of the character at all, but they're targeting the skeletons. And then the skeleton is then associated with the 3D model. So for a character, you have to have both a skeleton and a mesh that shows you what the character actually looks like with all the materials and stuff on top of it. And then when you bind these two together, you can now animate the skeleton and the mesh will move with it. And this is actually very carefully done. Like you actually have to tell exactly the system what parts of the mesh are affected by this bone and what parts of the mesh are affected by that bone and so on. So this, what is called a rigging of the model, can be a tedious process where you're trying to match up the skeleton and the look of the character. And then, but actually, the way that this is then rendered, you want to rely on the fast rendering of triangles in the low-level renderer to actually render the final mesh in the right place, given the skeleton. So the communication between the skeletal animation system and the low-level renderer, you can just give the low-level renderer the skeleton, and then just say, and here's the associated mesh, and the low-level renderer can actually do all the transformations required to move the pieces of the mesh into the right place and do the animation really fast. And this was the only way that it was even possible to get such high quality animation that was affecting so many vertices in the models, was to rely on the GPUs to do a lot of it's called the skinning of the model, rather than having to do it on the CPU. Now, so yeah, we have this skeletal animation system there to do these character animations. Um, Although many of these animations come from files that you just read in from disk through the resource manager, some of these animations are coming from other subsystems. So the physics subsystem, for example, that is a system that would maybe configure those skeletons based on forces in the environment. It was a really, so in the Unreal Engine, I just remember when the Unreal Engine was like really the first engine that provided this, what they called ragdoll physics. And what it means that like you actually animate, all of the characters were animated using keyframe animation in that game. They carefully made really nice animations for, like, I don't know, running and shooting and jumping, all this stuff. But then at the moment of being hit by someone else, they like quickly switched over to the ragdoll physics, which then took over the skeleton of the character at that moment, and then calculated like, here is the force of the hit, and here's gravity and all of the things around you, and what does that mean for your skeleton? It means that it like the force throws the skeleton in this direction and then it falls down, and all of the limbs are kind of, I don't know, no longer under the control of the character, but just the forces. And you would end up with things that looked quite spectacular. Like, I guess for the people that were playing first-person shooter games, it was really gratifying to see it, I guess. Like the enemies sort of like being like thrust away in some weird configurations into the air, but sometimes it also looked really ridiculous and kind of funny even, because you could get positions of the skeleton that were like impossible. So people just had fun with this system. But it's still there, I think, to some degree. Although people probably have improved a little bit the modeling of what kind of physics are possible with the human body. So yeah, this is a part of the physics and collision engine here. Speaking of the collision and physics, actually, collision and physics are two different things. Collision is just a check to see if you're colliding with another object. And in fact, having a system that can check really quickly whether you are touching another object, it's absolutely crucial. I mean, I don't think you can actually have a game if there is no collision checking. I don't know, can you think of any game that would like not have to check if you're colliding or someone is colliding with something else? Alone in space. How long can you survive nothing? Basically, that would be an amazing game. Um, but yeah, but then like as soon as you have something floating towards you, you want to see if you are like you can touch it or do something. Like I think every single game has the player at least interact with other things. Like even if you're throwing something at something else, does it hit that object or not? Is an important question. Tic-tac-toe. Well, in that case, you have the user selecting a position. So maybe you have to like know where they're clicking on what square. So at the very basic, you have to see like this, but you know. So yeah, but things become a little easier maybe in 2D, and there's like a pretty straightforward way to do it. Things could become a little trickier in 3D and all that. But you still need that for interactivity. You need to understand what those points of interaction are, both between the player and the world, and also the world within itself, all the characters and objects inside the world. So collision is there, and then the physics can often come into play, like to resolve what happens when you collide. So maybe the physics can model the forces that play when you hit something and what that would mean, because the other object, you know, does that throw the other object away, or is the other object really heavy so you actually get thrown back? So that's the physics taking over at that point. So these systems are often talked about together. Now you have something really, so all this complex stuff here going on, it's really important that you allow for some kind of a subsystem here that helps you debug when things go wrong and just to understand what's going on. Something that is not necessarily visible or shown to the players in the end, but definitely for the developers you have to think about this. So like a console that you can open and you can just quickly see what's the status of all the objects that you might want to have special developer menus and stuff to bring in new objects and things, and all kinds of statistics being recorded and shown on the screen. Like what statistics are you sometimes looking at? I don't know if you sometimes turn it on. Frames per second or things like that. You just want to see like, am I like totally like are a lot of frames being dropped here? Lag with in communication, maybe networking. Like what are the performance metrics really for that game at the moment? And those things can be logged out into log files, and maybe like special events can be kind of tagged in some way, so you can see okay, every time it drops below this, I want to be notified. Now, there are some even more complex things that are being done in the recording and playback. Um, so this has become really actually fancy now, where I think it's the PlayStation 4 that is constantly recording from your screen. At least like 15 seconds of everything that goes. It's like a buffer on there that remembers the last 15 seconds of what happened on your screen. I don't know about privacy actually. I don't know. It's like everything you do there is actually being recorded all the time. And when there is a core dump, if something crashes, those 15 seconds of what was happening on the screen is actually stored with it. So if there's an error, you can submit the whole thing to Sony or whatever, and they can actually see, oh, okay, this is what was going on when the whole thing crashed. Sometimes this is like in this case just like the video grab from what's going on, but you could also have playback systems that remember where all the objects are and kind of can recreate that scene um, just in the simulation. It's like setting the simulation to the state that it was in when everything crashed. So that's also possible. All right, so moving up here to the right, multiplayer things, multiplayer things. Well, the thing about multiplayer, there's all sorts of special considerations that come into play when you have multiple users in the same world interacting. And also, like multiplayer, what kinds of multiplayer are there? I mean, I'm not talking about the game style. I'm talking about like physically almost. Like how do you set up a multiplayer game? Sorry? Yeah, peer-to-peer, like, yeah, we can think about that, how the networking is done. But even like, before we talk about networking, just how the game supports multiplayer, we can talk about games that support like even like multiplayer on the same screen, for example. So there will be no networking involved. It will just be that you can have like two characters on the same screen at the same time, two controllers connected at the same time. Or you can have split screen when you actually put them into separate viewpoints. So there being local multiplayer, but then you have network multiplayer, yeah, and then you can think about how you connect them together over the network. Sometimes just a few people, sometimes like massively online multiplayer games. So these have different requirements, and you want to have some kind of a capacity in the engine to deal with these things. And it turns out that it is very hard. It's very hard to add multiplayer after you have developed a single player game. If everything has been done with a single player in mind the whole time, and now someone says at the very end, oh, by the way, we want multiplayer, it's a major hassle to take everything apart and think of how every single thing in the game would be shared with someone else, no matter how that would be done. But the other way around is easier generally. So if you design and create the engine with the idea that it would support multiplayer, but then in the end they say no, drop the multiplayer. Well, no problem. You, it's just basically like you are alone there anyway. So some of the games like Quake and those games, they actually just always run in a multiplayer mode, even if you are playing by yourselves. So there is actually a server and a client on the same machine talking to each other while you are playing all by yourself. Um, yeah, the things that are in there, if you're wondering about the specific text that it says in there, object authority policy, it just means like who has authority over a specific game object. So if there's a game object in the world shared between a lot of different players, what player has the authority to, let's say, delete that object from the world? That's very important. Like, does everyone have that right or not? And it would be really bad if someone else had the authority to like take you out of the game, for example. And game state replication is, of course, just making sure that they are synchronized across different clients. Okay, so moving to the right, even more audio. Audio is sometimes forgotten completely in game development. It's like kind of sad. And as the Station says here in the book, that he is quite familiar with the situation where game developers don't even like, they actually never turn on the sound. They're just busy writing code to animate and make all these characters come alive and all this stuff, but they actually don't know what the whole scene sounds like. So that's a a bad thing that because the sound is obviously such a huge part of the experience and should be considered at all stages throughout. And here we have a few boxes that have something to do with sound where you have, well, so on the bottom box there, audio playback and management, it's it's like the basic thing about just being able to play a file, even like play music files or something like that. But then you also have some very interesting specialized things which have to do with localizing sound in 3D. That is not particularly easy. I mean, I was reading about the first Thief game because there's an anniversary of the Thief games, and audio was hugely important in the first Thief game, which is kind of the first really like stealth type of genre game, and sound was so important. And they actually built into that system, even if it's a 20-year-old game, they built into the system sound propagation. So actually, like walls and doors would muffle sounds quite realistically, and you would have to get really close to doors to hear what's on the other side and so on. These are not trivial things. So having a special subsystem take care of it is really, really good. You might actually be able to get some third-party tools to help you out here. Also, different effects. So DSP just means digital signal processing. So you can take any sound, anything off your disk, whatever, and then stream it like through an effect box, and they could do all kinds of things like changing the pitch and things like that. So you could change the way that voices sound and things like that, or make one effect that is very like popular is to make a little bit of an echo of your sounds. So if you are walking inside a room or a hallway, then it echoes a little bit more than when you walk outside or into a small room, and that could be done with a digital effect like that really easily. So there are things to consider over there. And lastly, in this slide here, we have the human interface devices, which is the controllers that you have. This is like basically the input output. Um, Human interface devices that have like okay, joysticks and such. They're not just input devices. So don't forget that you can also push things out to those devices, like making them shake or have some light blink on it, or even like sound come out of the controllers. So these can be quite complex devices to deal with sometimes. Um, Things that also like you can have force feedback, literally, where you like lock a steering wheel because you cannot turn it anymore. So yeah, you might have to build a whole subsystem dealing with those types of issues. All right, so that's the central part there. Pretty big piece here. So now we are uh, up to towards the top of the game engine. This is really like the edge of, maybe this is the top edge of the game engine itself. So we've talked about a lot of specialized things underneath specialized subsystems, but where it all comes together is where you actually make the game. So what do you have to provide to the game designers and writers and programmers to put the game together? You have to come up with like, usually there's like a scripting system of some sort where you can describe the world and describe the rules of the world and describe the mechanics, the game mechanics of the world, like the goals of the player and things like that. How do you express those things? And you can express them in terms of objects and characters being interacting and things like that. So um, the whole world is usually it's called like it's it, the whole world is described in an object model where all of the objects of the world have been brought together and explained. And we'll talk about object models later and actually different ways of implementing object models. Some of the objects in the world are going to be static objects, and some of them are going to be dynamic objects. Um, the objects in the world, they might have to interact with each other. Most likely they'll have to let other objects know what is happening or whether they want to do something to them or whatever. So there has to be an event or messaging system in place. And it could just be as easy as an object maybe broadcasting some message, and then everyone in that room can hear that message and respond to it. Or you could target a specific object and say, I am talking to you, and I'm just reduced your health by this much, so do that for me. We can talk together like that to a system like this. Event messaging, I mean, there's not a huge difference between the two. It's basically just a communication mechanism and loading the world. But the scripting system that is there that allows the game designers to write up all of this logic and tie everything together. Sometimes this scripting system is a special scripting system that you invent. Like you come up with a language that you provide to your game developers and designers. And the Unreal Engine, they had something called Unreal Scripts to do this, to make these make new games with. So you had to learn Unreal Script, which was a little bit like C++ in many ways. Then they kind of replaced that system with blueprints later on. They changed that scripting system from a programming language looking thing into a visual language. So the scripting system in Unreal is now just boxes you sort of connect with lines. It's kind of cool. I mean, they're trying to make it more accessible to maybe people that are not programmers to set up the world. there might also be some kind of a support there for high-level game flow systems, meaning that maybe there's some way to sketch out, let's say, to quickly put up a flow diagram, a state diagram. For example, you might just want to quickly say that for every character in the game, they can be in the idle state, and then they can transition into defense states or something like that if someone comes close to them. So you can quickly be able to do these two boxes and say, okay, they can be two states, and you draw an arrow between them, and you transition when this event occurs, which is the approach of the player. So doing that using some kind of a support for state machines is kind of nice. Or even like higher level decision-making systems that the AI might want to use, like behavior trees or something that are quite popular now. Those can all be supported in this gameplay foundation layer here. So this is the capacity of, this is sort of like what really brings everything together and makes it into a proper game engine that is useful. And then really on top of this, we are mostly outside the scope of a general engine, and we can start building parts of a game. So some of these may or may not be considered part of a reusable engine. The literal player mechanics, how the character moves around, like also how the camera moves with the player. Is it this type of camera or that type of camera? How is it linked to your movements? You can solve that per game. The AI can be also something that is specific to this particular game. Is it a sports game with this type of AI? Or is it a real-time strategy game? Well, it's maybe kind of a different type of AI. Some of these things can be reused, but often these things are tailored, especially because you have to optimize things, so you don't want to have too many unused things lying around. And you also now know for sure what game objects there are. So you have narrowed the scope of game objects to maybe several basic classes of game objects, like weapons, power-ups, vehicles, and so on. So you have created specific types using those scripting languages and object representation languages. So that's the very top there. So now we have managed in not too long of a time to pretty much go through this all the way from the bottom all the way to the top, where things above depend on the things below, and obviously the game at the top is depending on all of the other stuff being there below, and even like the gameplay foundation part really has to be in place before you can make the game. So on. This is all connected. But I want to hear from you. Have you now seen any are the boxes that we did not cover from when you were discussing this earlier. Do you, if you maybe quickly look over them, uh, is it something that does not have a home in this picture of this overview? I mean, there's no wrong answer. I mean, just throw something out there if you have, or maybe something that, yeah. Sorry? Yeah, the AI, the whole AI part. So like how much you would actually maybe have insight. So what kind of thing would the AI box do? Pathfinding, yeah. Where would you put pathfinding, for example? So being able to tell a character to say, okay, yeah. There's also another question from Akira about the AI. Yeah, exactly. So I mean, you want to be able to tell a character go from this point to this point in the world, and then solve that somehow to bring it from that first point to the second point. So that is certainly something that algorithms and AI can solve given the right representation of the world. So it does rely on a representation of the world that you can use for the AI. For example, that you might have to do a navigation mesh for the world. So then we can bring the question to where does the navigation mesh come from? And that's a good question. It might It is possible that the navigation mesh, which is like the navigatable part of the world, um, would be very different between different genres of games, or the how what the world looks like. Again, maybe whether it's an outdoor world or inside, or what kind of detailed movements are you concerned with. So some people might argue that you would pull all of this up to the top and say like, well, it's a very specialized type of movement thing that you have to do for this type of character or this type of vehicle or something like that. So you optimize it really right there at the top for that thing. Um, Others might say that like, well, come on, I mean, like the basic idea of a navigation mesh is pretty generic. So they might want to put it down inside that you have an AI box in here, somewhere around here, that is capable of representing a navigation mesh, and maybe even a navigating agent that is capable to traverse that mesh. But they would then have the capacity to define that mesh any way you want. Like it could be a grid, it could be a collection of polygons, it could be something else. So you might have this way of being flexible enough, and then up here just tell it which one to use. So yeah, I think more and more we will be seeing things like that happen. That you would have good solutions to these things, and you certainly have game engines that do provide this functionality today, like the navigation mesh and the pathfinding. So yeah, I think I agree with you that this would be something nice to have in there. Some of those things were brought into this picture through the third-party SDKs and say, well, okay, if you just use key maps, it doesn't exist anymore as a package for some reason, but there was a solution that Autodesk was sharing for a while that you could just bring into your engine that did exactly this, did navigation meshes and pathfinding. This might also be a good opportunity for you to think about, like, maybe you have a career and a possible career in making these useful tools for game engines. And there's certainly a need for some of these. Any more? But okay, so we were somewhat complete then, I guess, in this. But you can keep thinking about it. You can keep thinking about like alternatives to this setup or this approach. But we will now later in the course go and dig into some of these boxes a little bit more. The last thing I wanted just to mention before we break here is this part of the game engine. Well, I don't know. Maybe you don't really specifically call it a game engine, but it's still a part of using game engines. and that is what is called the asset conditioning pipeline. What this means, it's a weird name, but it's basically how do you bring assets created in other tools into the game engine? Other tools meaning things like 3D modeling packages, sound editors, and so on. Because those tools, which are on the left here, they are proprietary tools with their own formats or whatever. They don't concern themselves too much about your runtime requirements or your game, specifically. So they have ways of dealing with these assets that are not necessarily compatible with the game that is going to be running over here. So the conditioning pipeline is the pipeline that takes those assets and prepares them for the game. And those can be several different steps that you go through. Um, Maybe like completely changing formats, optimizing the formats and stripping away stuff that your game doesn't care about. Combining things. I mean, you need to combine things like textures and meshes at some point to build a character, for example. So those are some of the lines that come together here. The dark lines are actually just where the data is flowing and it ends up in these storage bins. But then the light lines say that, okay, this storage bin is actually referring to that other storage bin in order to make something. So those things are all connected. And in the end, you have some kind of a game world and game objects that are put together from all of these different assets. And we will talk about a little bit later also about this part. And I want to open this also for you, if you're thinking about like a final project, which is something you can pick in this class, you can decide to, of course, as your final project, you can pick any part of this as something that you would like to work on and make or something like that inside the game engine, but your final project could also lie out here. So maybe your final project is a piece of the asset conditioning pipeline, something that takes an asset and does something with it, allows you to maybe modify or edit it or something, and then bring it in. Ogre comes with some tools like this, and so you already have a little bit of an asset conditioning pipeline that is part of Ogre, but it doesn't necessarily cover everything, and so you have an opportunity to maybe bring in other assets and work with other assets. Okay, so I think any questions about what we were discussing today? I know that we will be in communication about the first lab, of course. We can use Piazza. There's already a couple of questions there, so please go in there and see if you can also help each other out as we're getting closer to actually finishing that first lab and getting that up and running. Any quick comments or questions now? Or something that is like a burning question? You can just take it online then. But then, okay, so we'll meet here again on Wednesday. Everyone sign up on that sheet. Everyone, okay, you're missing, so you have to make sure you get the sheet. So then I'll see you on Wednesday. Thanks for today.